So for today's tutorial, we'll be looking at a linked list. So a single linked list with an iterator, as I believe Professor Coulter has done in the last couple of lectures in class. So if you've attended those, you'll know pretty much exactly what we're doing. But then you can use this for revision. But if you haven't seen those, then please just ask wherever you might be unsure about something, and then we can take a look at that. So I'm pretty sure you've already done the theory about all of this in class. So I'm going to just kind of quickly go over what we're trying to do with a linked list today. So for a linked list, assume that we're doing a single linked list. So each node is only, it only knows where the next node is. It doesn't know about the previous node. So in our data structure, we will have some node, and let's for now just, we don't care about what's inside of these nodes, and I should say there's 3 elements. So there's some node, and this node knows about this one, and this node knows about this one. Actually, I want to draw this line inside here because something in. So what we know from what we know with points and all of that, that something must store this information. So something in, let's call this node 1, node 2, and node 3. So something inside node 1 must tell it where node 2 is, and similarly something inside node 2 must tell it where node 3 is. And then at the end, how do we know, how does node 3, like what does that point to? Well, this just points to a null value telling us that we've now reached the end of the node or the end of the list. So this is what our single linked list looks like, but then we also want to store some value. So essentially what we'll have is we'll have some data or element or value or whatever the case may be. So let's just call it D for data. So each of these, so node 1 now stores value D, which it could be an integer, it could be a character, it could be a string, whatever we want to store within these nodes. In our case, for today's example, we'll make it templated, so this can be whatever. So it's the value data of type T, which we'll draw in here as well. And then this over here points to, not the value, sorry, so I'm sure if this is a bit unclear, but it points to the next node. So this entire thing over here is what this arrow is pointing to. It points to this entire thing, the entire node. So this is essentially just a, and we'll call this like an end, so this is just an end and whatever. So this is a pointer to some node, and we'll call this one next. So this points to its next. This one is also a pointer to some node called next, and this one is also a pointer to some node called next. And in this case, the next node is just null. So all that node 3 knows is whatever, there's nothing next. It just points to null, and that's how it knows that it's the last one. And then this is what essentially the nodes in our list look like. So this is the list. However, this is only the nodes in the list really. We still, as a data structure that we want to use, we still need to store some other information. So what we might like to store is, well, where do we start? So if we're going to work through, something needs to tell us N1 is where we start. So we would like to have a head, and in this case, this will just be equal to N1. And then the head is also just a pointer to some node. It might potentially be worth it for us to tell us what the final node is, even though there's not really much value in starting there, but oh, just draw an n, it's n3. So this will also be a pointer to some node, but there's not really too much value in us telling us this is the last one. So we'll store it, but you'd mainly probably want to use this in a doubly linked list that will have a previous node as well, because then you can start at the tail and then go back to the previous one. But in this case, the tail will just always point to null. So we won't really be using this too much, other than to maybe add something at the end. So, but we'll get to insertions and stuff later. But in terms of just looping through it, we're not going to start at the tail to loop through it. Then the other thing we might like to store is just an integer value length, which will essentially just allow us to keep track of how many elements we have in this, and that we can then use to see if our list is empty when we start with it. So if it's 0, then it's empty, and then also potentially it's 0 and remove an element. We want to add an element, whatever we know how big the node is that we are working with. But when looping through it, we don't even have to look at how long it is. So let's say we just want to get all of the elements. We won't have like a for loop and check that it's less than the length or something, like we normally do for an array, because we know the tail points to null. So as soon as we get to a node that points to null, then we know we've reached the end of the list and we can stop looping. Okay, so let's start with implementing just this list, and then as we add functions, I'll come back to this diagram and kind of show what we're doing with it from like a visual standpoint. So I just made a normal console application, so see everything's still working fine. And like I said, we'll be using templates today, so we'll have a header file and an implementation file, so IMP, instead of the usual CPP file. So in this case, we'll call this one linked list .h for our header, and actually that's all of them, and it's even here. So we'll have a header file, and then I'm just going to create the implementation file so long, just so that we have it. So an empty file is, and this one also be named linked list, but then .imp. Okay, include that in all of them, and we're good to go. Okay, so inside our header file, when working with the implementation files, we need to add that at the end here. So include, and then linked list with not.h.imp. So this will just make sure that this code and implementation file is compiled with everything in our header file, and then we can start with our template. So template, sorry, not subname, template, and then type name t. Once again, you're free to use this, or to name this whatever you want, but we'll stick with t just kind of for the consistency sake of it. So type t, and then we have our class called linked list, and our linked list will have a public and a private. Public and private. The private will then store the information such as the head and tail and all of that. But before we can do that, we need a structure of what this node is. So if we go back to our diagram, a node consists of some data type, which is templated in our case, and then it consists of a pointer to another node structure. So we can do that at the top here, and we'll say our struct node consists of, and this should also be templated, so template type name t, because we are using, this was actually storing the information, so this will just assume that the node will have the same type as whatever our linked list is, and in that case it will just be a type t data. So this is what we're storing of whatever data type we use, and then we have a node which will be of the same type, and it's a pointer to that node, which we are calling next. So this over here refers to this picture that we have here of just this node with its data of type t, and then a node pointer to the next node. So that's what every single one of these are. So when we've got this, we can let's start with our private variables, because we know what they look like. So we want a head, a tail, and a length, and these are both node pointers, the head and the tail, and the length is just an integer value. So we can have, let's start with int underscore length. Okay, now hopefully I'll keep spelling it correctly throughout this. Last time we had templated classes and me trying to type length, it ended in disaster. So type t and a pointer to that, which we will call head, which is just the first node in our list, and then type t pointer, which we will call tail, which is just the last node in our list. In this case, they happen to be node 1 and node 3, but we won't set this in the beginning. We'll set this as it is updated. It's very seldom that you'll immediately know this is what everything in the list, and you set the node then tail afterwards. You'd rather start with an empty list, and even if you know which elements you want to do, just insert them depending on the order at the end and at the front, and then just that way update what the tail is. So that's everything we need in here for now. We can then have our normal constructor, so a notice constructor that will essentially just set the head and the tail both to a null pointer and will set the length to 0. Then we might have a linked list constructor that takes in a default node. So it will take in a node of type T, and we'll call this node default. So maybe we set the size as well, and then we go through that. Really, I think the easiest would just be saying that there is one node that is a default node in here. So we'll just insert to the back a new node or something that looks like that. I'm not sure it will do with that yet, but like I said, it's very someone will know from the beginning what everything inside the list is going to be. So probably won't use that too much. Constant. So a copy constructor for the linked list, which also type T. You have to pass that anyway, linked list, and we'll call this object original list. And then we want to have a destructor, so linked list. This will just set every node to null. This won't be the same as deleting an array though, so it won't say, just say, for example, so we won't say delete and then in square brackets our list of nodes or something like that, because if you see here, we don't actually ever store an array of these nodes, we only store the head and the tail. So we'll have to start at the head and then go to every single node and delete it. But we'll get to that when we get to destructor, and then let's have some overloaded operators, so operators, and we'll just have one. We'll have a linked list or return a, so it'll just be an assignment operator, but let's have T and the assignment operator, which will take in a constant linked list of type T, and we'll call this object right hand side. And then just for the ease of use here, we will have a so later with the iterator, we'll be able to print the values inside the list as well through the use of the iterator. But just to in order to test our list before we have the iterator working, we'll just have a print function as well. So print, and this won't change anything, so it'll be constant. This will just loop through it and just put everything to the standard output stream. And then we need the ability to insert something into our list. So insert to list, and we can add either something to the start or the end of the list. I'll show that on the diagram in a second. But void insert first, and this will take in a value. So we don't need to give it where the next node or something is, because we can only add at the start or at the end. We could theoretically make it a bit more fancy and say, okay, insert after whatever element has some value. So then maybe we give it a value, and then so like we give it like an index value or something, and then we give it the actual value, and then we loop through every node and we say, okay, well, if you are equal to that value, then let's insert it over there. And that way you could maybe order the list, or like insert after or insert before, and then we give it a value and then the dates where you want to add. So we could maybe do something like that as well. Let's see if we finish up with everything else before our time's up, and then let's maybe get back to this. There's something to look at, and then that should be it for now. I think just to make our life a bit easier with the constructors, we'll have some helper functions. So helper functions, and this will just do one to free the list, and then one to copy the list. So copy list, reason being that we're not going to, and it should take in the same parameters as up here. So a constant linked list of type T reference, and then object original list. Okay. The reason we're not going to bother with like a setup list or something is it's not the same as with the 2D arrays where you have to loop over it and then set values, like assign memory and then set values and all of that. Initializing is very simple. You just say, okay, and then and the tail both point to null and the length is equal to 0. So it's not much to done there. So let's copy all of this into our implementation file, and then we would also like to copy our helper functions in as well. I'll just put a comment here, helper functions, and everything up. Okay, so everything in the template class does need to have the template in front of it. So template type name t. So let's add that to all of them. It's always a bit tedious, so let me just actually first space everything out nicely. And then we can just add these in. First, insert last, and then our helper functions. Okay, and then we also want to say colon, and this will be a linked list, or it belongs to the linked list class already, and it is also of type T. So C colon, and then the function name. So add that everywhere, keeping in mind to add it not in front of the return type, but in front of the actual function. So in front of the operator, in front of the print, in front of the insert first, insert last, free list, and copy list. And then, last but not least, just add our brackets at the end of everything. So it's brackets, 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 and brackets. Okay. But you can finally actually start coding on this. And like I said, the basic constructor will be very, very basic. So we'll just say that the head is equal to null pointer and the tail is equal to a null pointer, and then the length is, oh my god, okay, there we go again. And the length equals 0. So let's double check that this is spelled correctly. So length and length. Okay, seems to be. So let's look at what this is doing. So the initial, the inner constructor will essentially leave us with a head value that points to, so head is equal to null, and the tail is equal to null as well. So what this means is that there is no node. So there's no first node or anything. So if you were to go into the list and say, okay, loop through it or whatever, the initial node, it would, in our loops, we would first check, does the next node equal to null? And if that is the case, then we will just say, okay, well, we could maybe have a check that just says, is the length equal to 0 or whatever. So in this initial state, there is no node. Like there's not a single node that exists for this to point to. So it's not like there's an empty node or something. There aren't any nodes. It's only when we then start with our with other constructors that it gets a bit more interesting. So in this case, we'll have a default node, and we'll just say that, and even in this case, there's not immediately a use for this. So we'll just essentially say that the well, we have the node. So we want to make a new node that should be a pointer to a node, because keep in mind all of these want a pointer to a node, and this over here gives us some node structure, which actually also, this doesn't really make sense. So we'd rather have it start with maybe a value or something like that. So let's do that instead then. So I'm going to change this to rather take in a value of type t and a length of an integer. So num nodes. So we're rather going to do this because the other one doesn't seem too useful. And then let's change our constructs over here. But then this we will do after we have the ability to insert into our list. So for now, what we'll have, what this construct will allow us to do is to say, oh, we want a list of 10 values that are all equal to 1. Then we'll have 10 nodes that are all equal to 1. Or all equal to a, whatever the type is. I'm just referring to integers now, but it is templated. But we'll do this after we can actually insert something into the list, because we'll make use of that function for it. So then let's take a look at our copy constructor. So the way that'll work is, okay, well, we need to actually then do our copy list function that we have, which will work as follows. So all we want to do here is go through each and every single one of our elements that we have, and just essentially go through each and every single one of the original list, which we will start at the end. Let me just I'm going to move this up a bit. Okay, so let's see how we would copy this. Let's say we have we want to start creating this list down here, which is a copy of this one. We would start with the head node. So we'd go to our original node and ask you, what is the head? And then we'd get the head, and we would copy that into some kind of temporary node, or some kind of current node or something. And we would say, okay, take the head and insert this head into our new list. So this head would become node 1. So we would create node 1, and then we would go to the head and we would ask the head of the original list. So this is the original list, and we would ask that, okay, where does your next point to? So this head points over here, and we would take this and make that node 1, and then we would ask this head, okay, where do you point to? So it would go follow this path over here. Let me draw this in red. So it would follow this path, get to node 2, and then it would copy node 2 and add that in here. So it would put node 2 in here, then I'd go to node 2, ask where's your next, that would follow through, get to node 3, put node 3 in here, and then that would look for the next one, say, okay, that's null, and make this one also a null pointer. But this would already point to null because we're copying this entire node into here. So this node gets copied into here by our traversal. So the way we then end up doing this is we say, we make first a node pointer, so node pointer of type t, and this will be the current node that we're at. So whatever the current node, or the current node will be object original list dot head. So the current node that we are at is the head of the other one, and then we'll say while the current node is not a null pointer, then that means we're not at the end of the list yet. So node current is not equal to a null pointer, then that means we're not at the end of the list. So the way this works, so we first look at the next one. So let's say our node was empty, then both the head and the tail would be a null pointer. So it would immediately say, oh, this thing's empty, and then not do anything about it. However, if that is not the case, then we'll say, okay, this one is not a null pointer, so that means we want to insert it into our own list, and then we want to move on to the next one. So let's look at how we would do that. So we'll actually for this also use the insert function, because we want to insert that into our list. So the way this works is, like, we copy the consoles into here by saying that take your value and create a new node which will have this value in it as well, and then take your value, insert a new one that will have that value as well. Because otherwise, so this needs to point to node 3, and let's name these in red. So even though they are our first node, second node, and third node in the new list, they don't point to the same memory address. So if we were to copy these directly, node 1 would actually end up pointing to node 2 as well. And then if we were to copy this again, this would just point to that node 3, and so on and so on, which isn't what we want. We want it to actually point to the next node in our new list. So we don't want this, we don't want that. So it means we only want to take the value of it. So we'll do this, and I'm just going to make use of the insert operation so long. So we'll have an insert last from up here when we do actually get to it, but I'm just going to use it so long because what we want to do is we want to add whatever element we add at the end of our list that we currently have. So we know we'll use this. We just need to do the implementation for it still. So node current, and then take from the node current the data that we had, and then this comes back to the whole idea that node current should have been pointer as well, because whenever we have the star, then we have the arrow, and we're working with pointers here. So node current is that, and then node current then becomes the node current next node. So then the next node moves on, and we go like that until the next node becomes like, let's say this was the tail node, then its next is a null pointer, so then node current would be set to a null pointer, and then we would not actually end up going into this. So this is how the copy list function works. The way we actually end up using that is inside our copy constructor is we first then just create a normal linked list with everything set to 0. So inside our copy constructor, we say the head is null pointer, the tail is null pointer, and anything is 0. So now we have a new list which is completely empty, and then we say, okay, we want to copy the list of object original list. So what this means is we start with a new head and a tail and an empty list essentially, where everything just points to null. And then when we go here, we say, okay, we'll insert to the end of this list, whatever, and it will be up to our insert first or insert last function to actually check if the list was empty and then handle the way that works. If there isn't a node to begin with, then we have to create a node and do all of that. So we can kind of pass on that responsibility to the insert first or insert last function. Then, so we've done our copy constructor. We'll get back to this one once we have a better idea of how the inserting works. And then we've done that, and then we want to delete everything. So here we'll actually call our free list. Now, please note there is this built-in free list function, but this is with a lowercase l, ours is with an uppercase l. Also, I was being highlighted in green. So if we could have maybe named this something else, but in case you're coding now, just something like me going wrong, and then just double check that it's not that. So the way our free list will work is we will have to, there we go. So the way the free list will work is we'll start with the current node being set to the head. So we won't just start with head itself, even though the head, like, we'll essentially copy the head into the current node. So node outside t, and that will be equal node. And at the end of all of this, we can set the head and the tail to null. But for now, we don't want to do that. We want to first just say the current node is equal to the head, and this should also then be a pointer. Current node is equal to the head, and essentially while the current node is not equal to a null pointer, so the same as when we loop through it to copy it. So while node current is not equal to null pointer, then what we want to do is we want to, and the problem is we can't just, if we were to now, let's say we're busy going through this and we're deleting everything. If we delete node 1, we don't know where node 2 is. We then lose that ability. So we need to get node 1, then first figure out, essentially make sure we keep track of what node 1 is, or keep another pointer to node 1, and then we need to move on to node 2. So then we say, okay, this is now the current node, and then we can go and delete node 1, and then we say, okay, you are no longer the current node, you are now the current node. We can delete node 2, and then we can say, okay, you are no longer the current node, you are now the current node, which is a null pointer. So null is not the current node, then we can delete this one, and at that point we see, okay, the current node is null, so we've gone through everything. So the way we do that is we first say we need to get some temporary node that maintains which one has to be deleted before we move on with the current node. So a pointer to, and I'll just call this temp node, or node to delete or whatever, but essentially this is just a pointer to whatever node is going to be deleted now. And then we say, okay, our node current is now actually equal to the node current next node. So you get the next node, and then we want to delete the temp node. Now, the reason why this actually then deletes that node is because we are working with pointers. So this is a pointer to whatever node current was. So at this stage, before we run this line of code, node current and the temp node both actually point to whatever the head was. So if we delete it at that stage, then like the node current would also be deleted, and the thing that was the head and all of that. However, here we then change what node current is. Node current now points to a different pointer. So they are now or a different node. So it's a different pointer because this is also a pointer. So that's how they actually end up deleting that. So then we delete that node, and then at that stage, once we're done with everything, we can now say, okay, well, the head is now null, and the tail must also be null, and then our size must also be 0, so length is equal to 0 as well, because at this stage we've deleted everything inside of our list. So the tail is not pointer, and our length equals 0. So at this point, it looks as if we were to just do this, it would also look as if the list is empty, and there'd be no way to access the other elements of it. So it would act like an empty list. However, we wouldn't be actually clearing, like we wouldn't have actually cleared the memory, so that would have just stayed there. Okay, so now I can free it. Let's just double check if we actually use this up here. So we did say free list, and then the way it'll work for our operator is we will just first check that they're not the same. So if if we are the same as the objects on the right hand side, we don't want to do anything. So objects right hand side. So if we're not the same as the other one, then you want to free the list, and that's why the naming convention should be a bit different. But okay, so free the list, and then we want to do everything as if we're copying it. So we will just actually copy paste this code, and we'll set the head to 0, set the tail. At this point, the free list should actually have done all of this for us as well. So we can actually take this out, because if you see a free list, the last thing that does is exactly this. We can take that out, and then we just have to say, okay, copy the list and copy the list from object right hand side, and at this point we can say return this, and then we've got our operator working. So for the printing, let's do that as well, and then we just have our inserts left, I believe. And then we start to get back to that constructor. Okay, so for this, we'll loop through it the exact same way we've done for the other ones as well. So node of type T has to be a pointer, and node current, and that will also be equal to the head. So this will loop through it the same way we've done in the free list method, because this we also had to loop through everything, so it does the same thing essentially. And then we just say, while node current is not equal to a null pointer, then that means there is still something to actually be printed there. And then, okay, if we're going to make use of cout, we should include that at the top here. So include iOS stream, and also using namespace standard. Okay, so cout, and then we want to output the actual data value that we had at node current. So node current data, and add a space, and then we want to move on node current. So node current is now equal to node current next node. So that is now moved on one as well. And then at the end of all of this, we just inline characters, so inline, and that will output everything into a single line. Okay, let's start with the insert last, since that's the one we have already used. And then we'll just keep in mind here. So let me just delete everything and fill that in. Okay, so oh no, okay, there we go. So what we want here is we want to add it to the end of the list, because let's say we wanted to add the elements 1, 2, and 3 to our list. So we add element 1, and now we end up with node 1, which has the value 1 and a pointer to null, because this is the only node in our list. Now we add element 2. So if we add it at the beginning of the list, we're going to have 2 and then we'll have 3. So we'll actually have the list be backwards in terms of the order we inserted the values into. So we want to actually now add 2 at the end here. So what we need to do in order to achieve that is we need to say, okay, well, node 1, you now actually, instead of pointing to null, you need to now point, essentially this one here is at the moment the head and the tail both point over here. But if we're inserting at the end, we want to leave the head alone. It doesn't really matter what the head is, but whatever it is, we don't care what the head's pointing at. We're going to leave that where it is. So what we need to do is we need to create some new node. So we create a new node, which will now have the value 2, and it'll have a next value, which will also be null. And this one is now node 2, but it's not linked over here at the moment. So this doesn't actually know where it is. So so actually we should have started this if the head wasn't there. But anyway, so what we need to do then is we need to say, actually, the current tail, your next node. So the current tail is node 1. So you're saying node 1, your next node should now be equal to this new node. So then stops pointing there, and it actually, let's clear all of that, and it actually then goes and points to the new node over there. And then we need to tell the tail to stop pointing to that node and actually start pointing to our new tail node. And that's what needs to happen within every time we insert something at the end of the list. So once again, if we were to add a third one, we would make node 3, it would point to null, and it would have the value 3. And then we would first start by telling this one next node to stop pointing to null and to actually start pointing to node 3. And then we would tell the tail that you are now actually pointing over here. So that's what needs to happen when inserting at the end. If we were doing it, if it was empty, we would just start with the point where we would tell both the head and the tail to point to the node that we just created. So since at last, let's first create our new node. So node of type T should also be a reference and pointer new node new, and it will be equal to a new node of type T. And then we want to say, okay, your data will be equal to whatever the value is we just gave it. So node new, and then because it is points, we use the arrow. Data is equal to value, and node new next is equal to null points. The reasoning is because we're adding to the end of the list. So adding it to the last, which means it will just always point to a null pointer when it's at the end, because there's nothing after it. Now, just as the first case, if our length is equal to 0, then we just need to tell the head and the tail to both point over here, and then we're fine. So head is equal to node new, and the tail is also equal to node new, and else let's look at the else in a second. First, we need to know, so regardless of what happens, we need to increment the size as well. So our length is incremented by 1. And then what we need to do here is we need to say our tail is, so the tail's next needs to be equal to node new. So looking at this diagram here, if we were to add new one, the tail is node 3, and the tail, so node 3's next must be equal to, if you were to create it, node 4. So when we're referring to the tail, we're just saying actually this is node 3 or node, whatever the last node is. But that this tail also has a next, and it is this whatever the last one is. So this happens to that, and then we say the tail is now equal to node new as well. So firstly, the what used to be the tail now points to the new node, and the tail now is the new node as well. So that all gets updated, and then we've added something to the end of our list. Then inserting first, so this works very similar to what we've done over here, so still that. And the way that works is when we first create it, we need to also create, so if it's empty, we create an element, call it node 1, and let's also add the values 1, 2, and I can't count, so 1, 2, and 3. So those are the values we want to add into our list, but we're adding it at the front now. So I should have drawn this to the right, but that's okay. So we first create this new node, which we've done over here. We assign it its value, which will be 1, and we can cross that out because we've added it now. And then if the length is 0, we just say, okay, both the head and the tail, I'm just going to do a H and a T for now. So head and tail both point to this node over here, and this one points to null. Now we're going to add something to the front of this. So we create our next node, so node 2, and this one will have the value 2 in it, and its next, or its next node should actually point to, and in this case as well, actually, because when it's empty, the head and the tail are both equal to null. So this null that it points to is actually also the head. Both of them are just pointing to null. They don't really matter too much when it's empty. But when we create a one where it is not empty, we then want to tell this node, okay, you point to the head. So it points to the head, but then through that it's actually pointing to node 1. And then once this points to the head, we can then say, okay, the head should now no longer point over here. So the head gets removed, but this pointer still exists, and the head then actually points to node 2, and node 1 remains pointing to the tail. And then we add the third one, we say this is node 3. It points to, so it has the value 3, it points to the head up here. The head then no longer points here, but this still points over there, and the head now actually points to node 3. And what we end up here then is that if you were to traverse this list, we'd end up with the values being read as 3, 2, and 1, because we're adding stuff at the front. So to do this, we say node of type T is, with a pointer is node new, so we can name it down there as well, yes, and then we say this is just a new node of type T, and the node new data will point to, or will just be equal to the value that we've given it, so value, and node new next is equal to, and then the next, instead of pointing to a null, we will rather point it to the head value. So as you saw when we added a new node, we said, okay, you point to the head, which is then just whatever the head node was. You point to the head. So in the case where the list is empty, then head would just be a null pointer, so it would actually point to a null pointer like we said over here. However, in this case, actually head would have been pointing to the null pointer as well, so it would have pointed null pointer through there. But that's neither here nor there. So we've added the head, and then we say, okay, well, the head now actually points to the new node, so the new node. And then we say just reasonably just check if the length is 0. So if it's empty, then we want to add, or then we just want the tail to also point to this node. Because at the moment tail just points to a null value, but that's not actually the case. There is now a node in here. So if the length is equal to 0, then the tail should also equal node new, and regardless of what's happened, we should increase the length. Okay, so insert first, logic seems like it should be fine over there. Insert last, the logic seems like it should be fine. This seems like it should be fine, and that's all okay. Let's quickly do this, where you can add like some number of the same value initially. So essentially all we'll do here is we'll say, if we do give this values, let's start off by setting everything to null, and then we will just add everything. It doesn't really matter if we add it first or last because they all have the same value, but let's just add it last so it is done what we would consider in order. So for integer I equals 0, while it is less than the number of nodes that we wanted, it's plus, and then we can say add last, what do we call it? Insert last, I think. Insert last, and we just need to give it the value of type t, which we got over there. So insert last, the value, and then at the end of the day, we'll have a list that is however many elements long that have that value inside of it. Not really immediately useful, but it's a nonetheless, so we can understand what's happening there. Copy constructors then, feeding list, yes. Okay, all seems to be fine. So let's go into our main, and I don't think we're seeing anything over there. Okay, so inside our main, let's just create a list. We'll add elements to the end of it, and then we'll print all of it using our print function to just see if all of it is in there. Maybe it's just like our assignment operator or something like that as well. So linked list, and we'll make it a list of integers, and we'll call those object list. So no constructor over there, and then we say for, and let's just have also, let's just add, I don't know, 6 or 7 elements to it. So int 0, and while I is less than like that, and plus. Okay, so for all of these, so we'll also see the difference. So from what we know, if we add to the last, it should stay in order, and if we add first, it should reverse the order. So let's first add everything last and see if it works fine, and then we'll add everything. Last, and we'll add everything first to see if it reverses it as well. So let's give it the integer I, and then we can print the list as well. So print object list print, and then we can try copying a list. So we can say print list of integer, and we'll call this one our new list is equal to object list. So we use our assignment operator over here, and then we say new list print, just to make sure that this actually also works the same way. And let's just shoot output stream, say here keyed list line. Okay, so we expect the values to be the exact same for both of these when we run it. Let's see if we have any issues. We do. because we didn't include. So include linked list.h, and let's try it again. No, new list print and have, hold on over there, let's try it again. No, insert last is not declared in the scope, so yes, insert last. Okay, so 0, 1, 2, 3, 4, 5, 6, and the copies list is also 0, 1, 2, 3, 4, 5, 6. Okay, let's now go and change this to rather say insert first, and then we should see the order be reversed. So there we go, and then we can also maybe let's copy this, add it over here, and say insert last, and then we can see how it should go. So what do we do first? We first said insert first, so it first started here 0, 1, 2, 3, 4, 5, 6, and then it did insert last. That is well, but it didn't order, so it would say add 0, and then it would add behind the 0, then it would add the front to 1, and then add at the back 1, and then a 2, and then 2, 3, 4, 5, 6. So it would go like that. But if we were to have two separate loops, I think that would end up looking the same, because we would first add all of those to the front and then add all of those to the back. But it is actually done in order across like that. Okay, so at the moment we can do all of this, but ideally we'd like to also be able to actually access some of the elements inside of this list as well. So we'd like to be able to change whatever, like while looping through it, maybe we want to change whatever the value is at some specific index, and also maybe we'd like to get through it. So at the moment the only way we can actually do or see all of the elements is through printing it, but we don't have a method. So looking at our options here, we've got something to insert first, insert last, all of that, but the head and the tail are both private, so we can't access those from main. So there's no way in main for us to get the start of this list and then work through it. The only way we can actually see at the moment is through the print, which is now where the iterator will come in. So the iterator essentially will allow us to, the same way we have this for loop over here, we want to be able to say, okay, well, for all of the elements in our list, go through them. And we'll do it with the same structure. So overloaded operators will be able to say, okay, we've got some iterator. So instead of saying int I, we'll have an iterator, I mean the it or whatever, and that will be equal to the beginning of the list. And then we will say, okay, well, while this iterator is not at the end of the list, so that's the second part over here, so that condition. And then we also want to increment our iterator, so essentially loop through this list. So we want to be able to have a for loop like this for the linked list, in order to access and modify those values within our linked list. So that's where the iterator comes in. For the sake of, these are just going to do everything inside of the same header file and implementation file, but it could theoretically be a separate header file as well. This will just make it easier because everything will know about each other, but the iterator won't have to know about a list. The iterator only has to understand the concepts of a node, so that it knows that there's a next and a data value, but the list needs to know about the iterator, because a list will have an iterator. So we need to then, or not an iterator, it'll have the ability to return an iterator of the beginning or the end. So we will have our class iterator. Let's name it just something else. Iterator. Okay, so it doesn't care if so I'm going to have it with capital letters. So we'll have our class iterator, also templated, and this will also have a public and a private. So public and private. Oh, no. Okay, and then I put square brackets there, and all the private will actually keep track of is just a node that will start off pointing to the head, but it doesn't actually control the nodes in the linked list. So over here, when we point to a head, we actually later maybe have the ability to change what that head's next value is. We have the ability to change what the tails next node is and stuff like that. This one won't actually do this. This will just be a way for us to reference some node. So also be a node pointer node, but this won't actually control where these nodes point to. We will just use it to maybe access the values of it. So iterator, and we'll have a no-args constructor, and we'll have a constructor that takes in a node. So iterator node of type T. Oh, no, what have I done? Of type T, and this one will just be called node. And then we'll have a copy constructor, so iterator constant iterator of type T, a reference to that, and we'll call this object original. Then we'll have our assignment operators, so just go over here, iters, and we'll have an assignment operator, so iterator of type T operator, and iterator. I'll look the same as this. So if you want this iterator type T, and we'll just call this object right hand side. And then we want to have the ability to check if some value is equal to another one. The reason being that we want to, in our main, actually compare if we're at the end of the list. So in order to do that, we need to have the comparison operators. So it'll return a Boolean value, operator x equals, and this one can be constant, iterator of type T, a reference for that inside. So it'll compare if one iterator is the same as another, and we'll also have one for checking if it is not equal to some other iterator. And lastly, we want to be able to, we'll use the asterisk to get the element back, so, or a reference to some element. So the element, or the data will be of type T, so whatever that is, let's get a reference for that, and operator asterisk, and that will just give us, whenever we use the iterators, actually, it'll just give us whatever the current node's value is. It'll give us a reference to that, so we can go and change that value, or the data at the very least, but we won't actually be able to change where this node points to. It will just access the actual data. And then as in order to do it with the for loop, once you have the plus operation, so iterator T and operation the operator plus. So this one is for the prefix, so it'll increase and then get the value. Iterator 5T operator should have been plus, and this plus, as soon as we put the integer in brackets here, then this will now be for postfix. So this will first get the value and then increment it. Okay, so these should be all of the operations that we want for our iterator. Most of them are using overloaded operators, using that makes it easier to actually use the list instead of having like a bunch of methods for this. So let's go to our implementation file. It'll be done. We'll just do it at the bottom here. So iterator code, and add that over there. So all of this will need to have the same whole template thing above it. So let's first space everything out nicely. And that we want it over there actually. Okay, so template. template, template. It's okay, and this needs to, all of this needs the iterator colon, iterator of type t, sorry. So iterator subtype t, and there we go. T, okay, and then we need brackets to add another space there. E, okay. And I just realized that we don't have a semicolon there. So that should be all of this, and then we can get started with this. So very simply, if we just don't give it anything, we'll just say the node is equal to a null pointer for the node constructor. In this case, where we do give it one, we just say the node is equal to the node that we're at, or the node we were given. In the copy constructor, we just need to get the node from the original. So node is equal to object original dot node. Do we name an object original? Yes. So you get the node from over there. And then the same for the assignment operator. We'll say our node is equal to object right hand side dot node. We get that as well. And then over here, where we check if two of them are equal, we just return whether or not our node is equal to object right hand side dot node. And over here, we'll just see if they are not equal. Had this code been slightly more complicated, what you could have done is you could say just not and then this node equal to that node, and then it would execute this code and then just reverse the result. So if this equals operator is ever very complicated in your code, then you can do that over here. But in our case, it's very simple, so we're just going to change that. And then this, where we want to reference it, we just say, okay, return our node data. Data, is that what we called it? Yes, so data. So what this does is this gives us a reference to the data value of whatever our node was. Then if we want to increase it over here, so this one is the prefix, which means we want to increment it and then return. So if node is not equal to a null pointer, and that means there's something for us to increment, and then we say node is equal to the node next value. So what this does is, and then we can then go and return reference to this. So what we're doing over here is we're saying as long as this one isn't already the last, like the null points at the end of the node, at the end of the iterator, then we will say, okay, in that case, our node then just becomes the next node, and then we return this iterator. Otherwise, what we want to do is we want to first store what our current node was, but it will become the old node. So we'll have an iterator of type t, and we'll say this is the old iterator, which will be started with the node that we have. So we take our current node and create a new iterator which has this node that we're currently at as its node using our constructor over here. And then we say if, and then we just check the node again. So if the node is not equal to null pointer. Then we can say, okay, the node is equal to node as the arrow node next, and then we can return our old iterator. So return the old one. So we move it along, but we return a reference to this old one, but the node has actually moved on. Okay, so that's all the functions we need in here. Then we do need to allow our linked list to now actually make use of this iterator. Because like I said, the linked list needs to know about the iterator, but the iterator doesn't need to know about the linked list. So for iterator, we will just have an iterator of type t, and we'll just call this one begin, and we'll also have an iterator of type t, which we'll call end. So the begin points to, or this will give us an iterator from the head, and the end will be one for null pointer. The reason being that in the loop we can check if one iterator is equal to the end. So this linked list will have an iterator for the begin, and this iterator will be able to increment and increment until this iterator is equal to the end iterator, which is just pointing to null pointer. So inside our for loop, this is referring to an I can't remember I had that, but I just referred to the code command. So inside our for loop, that will be for this check. We will check that if the iterator is now equal to the end, which is the null pointer, then we stop the for loop. Otherwise, we increase the iterator, which is at the beginning, to move on. Okay, so to do that, we just need these methods begin end. They belong to the linked list. So this is the iterator code, this is the end of the linked list code, and then we can add this over here. So once again, all the template stuff, iterator, and this will belong to linked list. So linked list begin, linked list end, and a template for the end as well. Okay, and the way this works is this just tells us that to return, so we need to return an iterator, but this iterator needs to point to the head. So iterator of type t, and it needs to point to, or we need to give it a point to the head, and the node, the head node, and then this one needs to return iterator of type t that points to null pointer. So this actually points to essentially the tail's next node, is one way you could look at it, but the null pointer for the end. So what this allows us to do now is now we've got an iterator which will point to the head node, which is just the first node, and the iterator, it's easier to see over here, but the iterator has the ability to increment itself, so essentially move on to the next node, and it has the ability to check if it is at the end of the node or if it's not at the end of the node, and it has the ability to reference the data at whatever node it currently is at. So what that means is we can now use a for loop for our linked list that we had. So let's just see over here, we'll just say that we're now using the iterator, just so using iterator. Just so that in case we have some something up a bit weird, we can look at it over here. So we'll start with a for loop, and we'll say, okay, we want an iterator of integers, and we'll just call it and this iterator should be the object list dot begin, and this works because if you look over here, our object list has this begin that returns an iterator of the same type as the linked list. So we now have an iterator that has returned an iterator that has its node pointing to the head of our linked list. And then we say, okay, now we're looking at the second part, so the condition of our for loop, and essentially as long as we're not at the end, then it's fine, we can continue. So if the iterator is not equal to, and then our object list dot end, so this object list end essentially just returns an iterator with a null value, so null pointer, and what this does is it checks over here, is our node equal to that node? So if the node we have is equal to null pointer, and the right-hand side end is equal to, so as long as, okay, so in our case, the right-hand side here is this iterator end, and this iterator end is just the null pointer. So what our check is doing in that case, so the check just checks if the nodes of the left-hand side of ourselves and the right-hand side are the same or not the same. But in the case of our actual for loop, it's checking is our node not equal to a null pointer, and then if that is the case, then that means we can continue, and then we can increment our iterator. So what this is doing is iterator plus plus is over here, it shouldn't be the postfix, and we will just say, okay, give us the iterator value that we are at, so return that value, but then move the node on to the next one. So we move away from what the head was. So originally we have the iterator from the beginning, which is the head, but then this moves it the one next to the head, after that, after that, after that, until we get to the null pointer at the end. And then we can say, instead of having to use the object list.print. So instead of saying object list.print, we can now print this out just using our iterator. So we can now say iterator, and then we have to reference our, or use our asterisk operator. So this operator over here, which returns a reference to the value. So use our asterisk operator for the iterator, and we can add a space to the end of it. And then after all of that, we can add a inline, so it's inline, and this will now print it the same way we did previously, but we actually print it out ourselves over here instead of using this print list method. So this using iterator will also print this out, hopefully. Yes. So using iterator, and then it prints it out those values as well. However, what we can now also do, and let's just comment this out, is we can now actually access, because we have access to this value, we can change those values as well within our linked list. So what that means is we could say, okay, our iterator, so a reference to some value, is equal to whatever that value was. So we get this value again, and then we say maybe we add 10 to it. So this list should now add 10 to it, and then now we could print out the value as well. But to show you that it actually changed the values in the list, we're using object list here. So I'm going to say object list dot print, and this will now give us that same list, but with 10 added to all of the values. So there we go. We've now got 16, 15, 14, 13, 12, 10 instead of 0, and then 10, 11, 12, 13, 14, 15, 16 on the other side. Because using the iterator, we actually have access to a reference to the data within the node. So although we can't change what that node is pointing to using the iterator, we can't say delete some node or whatever the case may be using the iterator, because it only has access to it. Even though it has a reference to that node, we don't actually change what it's pointing to. We're not setting it to null or anything. We just have access to that data within the node. So whatever happens, our actual linked list structure. So in this case, it's using the iterator. We added 10 over here, 10. Whatever we do, node 2 will always point to node 1, and node 3 will always point to node 2. And this structure, or this flow of it, this flow of it will always stay the same when using our iterator loop through it, even though we can add values. We can change the value of it, because this value, regardless of what the value is, doesn't change. It's the second part of our structure that points to the next node, and we never change that using our iterator. Okay, so that is then everything that I want to show you today for linked lists with an iterator. I don't think there's really The only thing I think we can maybe look at is, like, say, deleting elements and so on, but I don't think it's worth getting into that for the last 10 minutes. So for everybody attended, thank you very much. I'm going to stop the recording now then, but I'll be available for like another minute or two in case anybody does have a question. Thank you very much.